Okay, welcome to the afternoon session. We have 3 papers in this session. And the first one is about the decision problem for regular first-order theories. And the talk is given by Umang.
Welcome, everybody. I'm Umang Mathur, and I'm an assistant professor at NUS. And this is joint work with David Mestel, who is also an assistant professor at Maastricht University, and my former advisor, Mahesh Viswanathan at Illinois. So for some of you, the title may sort of appear very complicated, and a large part of the talk will try to disentangle the complications in the title. And subsequently, I'll talk about the results of the paper and how they matter for PL research. Okay, so let's focus on the first part of the title, decision problem. If you have not taken any formal logic course, the decision problem asks, given a first-order formula or a formula in any kind of logic, tell me whether that formula is valid. So this problem has been sort of the cornerstone of foundations of both mathematics and computer science. In fact, Hilbert, in his list of many, many problems, the 10th problem, which is also one of the most famous problems, asks if you can basically come up with a finite axiomatization for the set of all valid statements in mathematics. And to be able to have such a mechanization, such a mechanical procedure, you basically need to solve this decision problem. Okay, so this was the decision problem, which was about a single formula. In this work, we try to generalize this concept, and we look at a more general question, which is, this time, you're given a set of formulae, which we can call a theory, and now you're asking whether this theory is valid. Now, of course, because so T can be possibly infinite, and the concept of validity of a set of formulae is not clear. So in fact, you can have 2 different interpretations for this. The first interpretation is that there is a formula in this theory that is valid, and the other interpretation can be that every formula in this theory is valid, right? So these are exactly the 2 questions that we study in this paper. A mild modification of the same question gives you this problem statement. It says you have a theory T, which is basically a set of formulae. Think of these as formulae on first-order logic. And the question that you ask is it the case that there is a common structure, first-order structure, that satisfies all the formulae in this theory at the same time, simultaneously? The other variant is the following. It says, is there a formula that is satisfiable in this theory? Right? If T was singleton, meaning a single formula, the 2 questions sort of are duals of each other, but not here. You sort of, an algorithm for the first question doesn't give you an algorithm for the second one. That's why there are 2 different variants. Okay, so that was the first part, the decision problem. Let me try to also detangle for you the second part of the title, which is about regular theories. So what is the regular part? The set T itself is what I'm talking about. To be able to understand what I'm saying, you need to understand that a formula is essentially a tree. Right? So over here, this formula says that the variable y is not equal to f of x. And likewise, this is a bigger formula, which I don't think I want to read out. But it's a conjunction of 2 subformulae, each of which have existential quantifiers. Okay, so now that you understand that a formula is essentially a tree, a set of formulas is a tree language. And you can talk about different kinds of tree languages. A very popular class of languages is tree regular languages, which is essentially those languages which can be represented using a tree automaton. That is, there's a tree automaton that accepts exactly those formulae or trees that are in your language. Right? So here I've not represented them as tree automaton explicitly, but even if you express these trees as context-free grammars, that's really an identical representation because parsed trees of context-free languages are essentially tree regular languages. So over here, the first language is the set of all formulae of the kind y is not equal to f raised to nx, where n can be any number from 0 to infinity. Likewise, the second formula is essentially a representation of something more complicated. It says that either y is not equal to x, that's one string, that's one formula, or the other formula is that, well, what does it say? So it says there is an x prime which is equal to f of x. So, and now inside that I'm re-quantifying x, and I'm saying that the new x is the older x prime, which is actually f of the older x. And then the remaining thing can be sort of recursively computed. So these languages are essentially tree regular languages. All right, so having understood the different parts, let's put them all together. The problem statement says you first fix a first order signature sigma, and you ask that, and now you're given a theory T over this signature. Now your question is it the case that there's a common model that makes every formula in this set satisfiable? And likewise, is there a formula in this set which is satisfiable? Okay, so why are we interested in this really obscure question? I just want to emphasize that this is not an obscure question. In fact, if you think about program verification from the perspective of algorithms, and if you let go of the syntax-driven style of proofs as in program logics or whole logic, the slightly different approach here would be to look at executions of a program and try to establish that each of these executions are correct. How does this go? So if I have a program here, and if I want to check whether it satisfies the following post condition, assuming the precondition is true, I can essentially put back the post condition as an assumption with the negation at the end of the program, and then ask whether any of the executions of this modified program are feasible. Right? So from program verification, I could translate it into a problem about executions, or set of executions. Observe that, at least for here, this set of executions is also a regular language, a regular word language. I can go one step further, and I can actually translate this problem into a regular first-order theory. So over here, I give you the context-free grammar for the same language. Observe that the set of formulae that this execution generates is essentially what you would get by performing a symbolic execution on each of these executions. Okay? So every execution corresponds to a constraint, and checking whether that particular execution is satisfiable or feasible is the same as asking if the corresponding formula is satisfiable. So bottom line, if you have the task of verifying a program, you can pretty systematically, mechanically compile it down to this problem of checking whether a theory is satisfiable. Okay? So that's a very natural motivation to look at this problem. And of course, this concept of coming up with the set of behaviors as a language and then translating them as formula doesn't really just is not limited to program verification. You can also apply the same concept to program synthesis. This time, your set of concepts is a set of programs coming from a grammar, and you'd like to see if there is a program in this grammar which satisfies the specification. This time, each program itself, you can think of it as a formula, maybe on a very different logic, or if the grammar ensures that there are no loops, then pretty much in first-order logic. And now the question again becomes a similar question about disjunctive satisfiability of a regular theory. Recent works have shown that, in fact, similar problems can be solved, problems around learning formulae from concepts can also be essentially translated into something very similar. So bottom line, even though this problem may look very unnatural, it actually is the most natural version that I can think of. Okay, so where do we stand? In this paper, okay, since I just have 5 minutes, in this paper, we're essentially looking at the computational aspect of this question. Meaning, given a theory, tell me whether the theory is satisfiable either conjunctively or disjunctively. Observe that even in the degenerate case where the theory is singleton, this is an undecidable problem. So the more natural question is, are there fragments of logic for which, if I give you a theory on that fragment, is the problem decidable? Okay, so this style of questions about what fragment of logic is decidable is not a new question. In fact, people in communities like LIX regularly ask that question. Okay? And one popular way of phrasing this question is to come up with syntactic fragments. For example, over here, this is the fragment of logic that contains all the formula whose pre-index normal form has quantified prefix exist cube for all exist star, and it has 3 relation symbols of arity 1 and 7 relation symbols of arity 7, and likewise the next thing tells you about the function symbols and their arities. Popular decidable classes for the usual decision problem are essentially encodable in this format. So the EPR fragment would be something like exist star for all star. You're allowed all relations, but you're not allowed any function symbol. Okay, so what did we find out? The very popular EPR class, which enjoys a lot of applications in program verification, quickly becomes undecidable when you ask the question in the context of regular theories. Okay, so these are both fragments of EPR, and they become undecidable. And that's because the canonical small model property doesn't really generalize to regular theories. So we had to sort of make that property much more specific, and we call it the bounded model property. We come up with 2 different variants of it, and we show that when you have any of these properties, you can actually show decidability, but for the more general question. In the interest of time, I'd not like to sort of go about the other ones. The 3 boxes with the syntactic fragments essentially make use of some version of bounded model properties. Okay, how much time? Sorry? Okay, so I do have some time. So if there are more questions and I don't have enough time, I'll ask you to just come back to me after the talk and we can take questions later on. So EPR, which is famously known to be decidable, quickly becomes undecidable because you can encode the post-correspondence problem here. This formula says that, so this formula only uses, this set of formulae only uses 2 predicates, S0 and S1, which are both binary. The S0 means the 0 successor, and S1 means the 1 successor. So you're essentially trying to construct these 2 strings and walk through them. And at the end, you'd like to check if the 2 strings that I constructed are equal. And that you can do pretty easily when you have EPR and sets of theories and sets of formulae. So coming back to small model property, which was the heart and soul of EPR decidability, the decidability really comes because of this small model property, which says that if you're talking about a fragment F, and if I give you a formula in that fragment, then checking whether that formula is satisfiable boils down to basically analyzing a bunch of models whose size is, upper bounded by some constant. Now, the nuance here is that that bound may be dependent on the size of the formula. Okay? In particular, for example, if you look at the EPR class, that bound is really the number of existential quantifiers that you have in your formulae. Right? Now, this doesn't gel well when you have an infinite set of formulae. So that's why we have to strengthen this condition. So the condition is pretty natural. You fix the constant a priori. Okay? Don't let it depend on your formula. And then you say your fragment is said to have this nicer property, bounded model property, if no matter what formula you take, independent of its size, the models that it can be true on, or the model that can witness its satisfiability, are bounded by that constant, which is independent of the size of the formula itself. Moreover, if this constant is also computable just based on the signature, that's even better. And that's the property of strong bounded model property. So where does this come? As in, where does this help? If you have a fragment which has this property, then the conjunctive satisfiability problem becomes decidable. And when you, on top of it, also have the strong model property, both these problems become decidable. Right? So what is the basis of this theorem? Before that, the two fragments that I mentioned in the beginning are really an outcome of these two meta-theorems. So what is the proof of why you get decidability when you have bounded model property? Essentially, the idea is that if I fix a model, then I can construct a tree-regular set of all the formulae that would evaluate to true on that particular model. Of course, the size of the presentation of this tree-regular set may depend on the size of the model, but if you fix the model, it's really a constant size automaton. And that gives you this intermediate property that if I take any theory, then I can, in a decidable manner, determine whether that model is going to be a common model for everything or a model for something in the language. All right. Now let's sort of quickly take a slightly now let's jump to the other decidability result that we have in the paper. It's about a semantic fragment this time. It's no longer a syntactic fragment. And the idea is to not restrict the quantifiers, but instead look at how the formula computes terms as you walk across the formula. And this is a good example because this is an example of what can go wrong. Over here, if you have a formula, you can essentially try to annotate that formula with what is the term corresponding to each variable at that particular node. And when you do that, you would like that this annotation is consistent across all the paths in your tree. But that may not always be the case if your formula is not a nice one. In particular, over here, over this path, there is a term that is being computed, namely f cube x 0. But as you walk through the path on the other end, in the middle somewhere, that term gets forgotten. There's no particular variable that stores it. So that's the recipe for disaster. You would not get decidability like this. But when you do not have these kinds of problems, you essentially get a very automata-theoretic decidability result. I will not go into the details, but the point is, such formulae are called coherent formulae when they do not have these bad paths. And you can also check whether a formula is of this kind in a very automata-theoretic manner. And that gives you the other decidability result, which is the more semantic one. So where are we? Well, I basically represented to you another connection between logic and automata and how it is applicable to many different applications in program verification, synthesis, and a lot more things in computer science. And where do we go from here? Well, the bare minimum question that we should try to address is there a more thorough classification of the fragments and whether we can actually translate these results into the applications of interest. So that's all. Thank you so much.
Okay, so unfortunately, there is no time for questions. So please switch to the next talk.